Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 3 of module 2, wherein we are discussing the aspects of electrochemistry. Friends, till our previous lecture, what we have discussed the representation of cell. We have discussed how to represent the half cell reaction or what are half cell reactions and how are they represented. We have also seen the meaning of EMF and how it is useful in determining the electromotive force of various half cells and how to represent them also we have seen. In this particular lecture, we will see now particularly to begin with the role of standard hydrogen electrode and how it is useful in representing or in aligning the chronological sequence of particular substance in a oxidation reduction potential series or oxidation potential or reduction potential series. Okay, so to begin with, we will start with the standard hydrogen electrode. Now, according to the convention, we have seen it in previous lecture that a half cell is called as the standard hydrogen electrode if I represent it with such representation. Now this particular figure represents the standard hydrogen electrode. You can see here that it is represented by this particular half cell reaction, that is the hydrogen gas in contact with the platinum electrode, and it is also in contact with the hydrogen ion containing solution. Okay, so this particular cell is assigned to have a zero potential at all temperatures corresponding to this particular chemical reaction or half cell reaction. That is the hydrogen ion in aqueous solution, it is consuming the electron and it is leading to the hydrogen gas. Okay, so the standard hydrogen electrode usually is consisting of a platinum electrode which is coated with platinum black, and the electrode is particularly dipped in an acidic solution and pure hydrogen gas is bubbled through it. So this is what is the construction of the standard hydrogen electrode. Herein we can see that this is the finely divided platinum coated on platinum foil. It is represented over here. Okay, now the concentration of both the reduced and oxidized forms of hydrogen is maintained at unity in this particular standard hydrogen electrode. Okay, what does this imply? This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in solution is also 1 molar. Say at 25 degrees centigrade or say at 298 K, the EMF of the cell which will gives the reduction potential of the other half cell. Now when it is connected to the other half cell. Okay, so this will give us the reduction potential of the other half cell because basically the standard reduction potential of this particular half cell is considered as 0. So if the concentration of the oxidized and the reduced forms of the species in the right hand side half cell which is connected to it, if both of them they are unity which is connected to this particular cell, then the cell potential is equal to the standard electrode potential of the connected cell or the given half cell. Okay, so if I would like to represent the standard hydrogen electrode along with some other electrode, so I can get the standard electrode potential as E standard is equal to standard electrode potential of right hand side electrode minus standard electrode potential of left hand side electrode. So this since on the left hand side we have taken the standard hydrogen electrode which is 0, so my standard electrode potential will always be represented by this. Standard electrode potential is equal to standard reduction potential of the right hand side electrode, that is ER, and since this on the left hand side there is a standard hydrogen electrode which is 0. Okay, so this I can consider. Now let us say we will take the example of two cells which are connected to it, because we are known to such familiar systems, and therefore let us take the example of this particular cell, wherein on the left hand side there is a standard hydrogen electrode, and on right hand side we have copper electrode in contact with the copper sulfate solution, or a solution containing the copper ion. Now if I measure the standard electrode potential of such particular cell, wherein the copper electrode in contact with copper and solution, it is connected to standard hydrogen electrode. If I measure the EMF of such cell, it comes out to be 0.34 volt, and this particularly 0.34 volt is the standard value, or the value of standard electropotential of the half cell, which is corresponding to this right hand side electrode reaction, isn't it? This right hand side electrode, what does it indicate? Because the concentration of right hand side electrode solution is again 1 molar, because we are assuming it as a standard electropotential, so concentration has to be 1 molar, and therefore this reaction is represented by this particular representation, that is copper ion, it is consuming 2 electrons and it is leading to copper metal. Now, the similar example can be taken like zinc. So, if I connect the standard hydrogen electrode to zinc electrode, which is in contact with the zinc ion solution, and if I measure the standard electrode potential, it comes out to be minus 0.76 volts. So, this minus 0.76 volts, it will correspond to the standard electrode potential of half cell reaction, which is represented by this particular cell reaction. Okay, so basically if you look at this equation number 28 and equation number 29, so in case of equation number 28, or this cell which is represent here in case of copper, the positive value of standard electrode, that is this 0.34 volt, this particular value in this case indicates that the copper ion gets reduced more easily than the hydrogen ions, and the reverse process cannot occur. That is, say hydrogen ions cannot be oxidized copper. Okay, so or alternatively we can say that the hydrogen gas can reduce the copper ion. This is the better way of saying it. So under the standard condition which is described over here, we can say that the hydrogen gas can reduce the copper ion. Okay, now therefore the copper does not dissolve in hydrochloric acid. What does it indicate? The copper does not dissolve in hydrochloric acid, whereas it can be in nitric acid, because in nitric acid it is oxidized by nitrate ions and not by the hydrogen ions. Okay, now let us come to this point, the second reaction, wherein we have considered the zinc electrode in contact with the zinc ions, and which is connected to the standard hydrogen electrode. So we get the negative value of the standard electrode potential, that is minus 0.76 volts. That indicates that the hydrogen ion can oxidize zinc, or zinc can reduce hydrogen ion, isn't it? So the positive value of standard electrode potential in the first case, what does it indicate? It indicates that the copper ion gets reduced more easily than the hydrogen ions, whereas the reverse cannot occur. And in this second case, the in case of the zinc electrode, the negative value indicates that the standard electrode potential in the zinc electrode indicates that the hydrogen ion can oxidize zinc, or I can say that the zinc can reduce hydrogen ion, isn't it? So that is what is the meaning, or that is what is the indication we can get from the this particular value. So negative value, whenever we get, it indicates that the standard hydrogen the standard electropotential, whenever it comes gives you the negative value, it indicates that the hydrogen ion cannot oxidize the given particular substance, and whenever it has a positive value, it indicates that it can oxidize the given particular substance, isn't it? Let us see, there are certain numericals, there are certain problems which are based on it. We can definitely approach towards it, but we need to see how this EMF can be measured. Let us proceed for it. Now look at this particular figure. Okay, now when the two electrodes are coupled together, a cell is formed. We represent each one of the electrode connected with the, we represent them as a half cell. So whenever two electrodes are electrically connected in combination with their solution, so a complete cell is formed. And this complete cell gives out the electrical energy in the form of EMF, isn't it? Now, on what account it gives you the EMF? Because there is a spontaneous redox reaction going on when there is an electrical connection in between the two electrodes. Okay, so this cell EMF is measured with the apparatus, and this apparatus is represented by this figure. That is the sketch is represented by this figure, and it is known as potentiometer. What is known as? It is known as potentiometer. So this potentiometer is based on the principle of compensation method or the potentiometer method, isn't it? So let us say that AB, this is a wire, and this we call it as a potentiometer, or this is a potentiometer wire which is connected to a battery C. Now, and this battery C, it has a high potential than both the standard cell, that is this, and the experimental cell, that is X. Okay. Now, what we will do to measure the EMF of the cell? First, a standard cell with EMF E is connected in the opposite direction by closing this key K1. Okay. The jockey, which is connected to the galvanometer, is tapped on the wire. Now we have to move this jockey on this wire. Okay, so now when we move this wire on this jockey on this wire, we can locate the point of null deflection, which will be detected by this ballistic galvanometer. Okay, now the point where we get the null deflection, we get the end point. Now let the point Y be the null point in this standard cell case. Now then this key K1 is open, and now we will lock down or tap down this key K2. That means the unknown cell is in circuit now. Okay. So the experimental cell with the EMF EX comes in the circuit, and the point of null deflection is located, which we can represent it by this Y dash. Now from this particular knowledge, we can have, that is E standard cell is proportional to length of AY, and E unknown cell is proportional to length of AY dash. Okay, so EMF of experimental cell can be calculated since the standard cell EMF of the standard cell is known to us. So we can take this ratio and we can find out the EMF of the unknown cell, that is EX is equal to length of unknown null point detection, that is AY dash upon AY into the known EMF, isn't it? So this is how we can calculate the EMF of the cell in laboratory. So this is that way the easy representation of the potentiometer. Although there are certain challenges whenever we perform the same experiments in the laboratory to calibrate the potentiometer and to find the null point in the galvanometer, it requires certain basic skills. Okay. So this is how simply theoretically we can estimate the EMF or measure the EMF of the cell using the potentiometer. Nowadays there are the electronic potentiometer which automatically detects the potential of the cell, whereas in earlier times there were a potentiometer which are called as vernier potentiometer, where one has to rotate this jockey over the wire to find out the null point. Okay. So now we will apply the knowledge, whatever we have understood in previous lecture and this lecture, to evaluate the EMF of the cell. Okay. Now let us take this example. In this example, there are certain cell reactions are given. So we need to write the cell reaction and calculate the standard EMF of the following cells. And what we have been given that the standard reduction potential of the electrodes are like the standard electron potential in case of aluminum is minus 1.66 volt, cadmium minus 0.40 volt, zinc minus 0.76 volt, copper 0.34 volt, silver 0.80 volt, and standard hydrogen electrode, that is 0 volt, that is standard SHE, standard hydrogen electrode. Okay. So let us proceed with this solution. So what we need to do is we need to first write down the cell reaction. So how to write down in case of, say, in case of zinc, if I would like to write down zinc cadmium cell. So the first representation is zinc in contact with the zinc ions of 1 molar, because it is a standard potential. So standard reduction potential is given, and therefore the concentration must be of 1 molar, and which is in contact with the cadmium electrode, which is put in cadmium ion solution, and both the solutions, they are connected externally, internally by salt bridge. Okay, so zinc dipped in zinc ion solution, and cadmium electrode dipped in cadmium ion solution. So now at anode, what must be, because left hand side is anode and right hand side cell is cathode. So at anode, what is happening? This zinc is releasing 2 electron, and zinc ions are releasing into the solution. So oxidation is taking place at this particular electrode. And what is happening at the cathode? These 2 electrons are getting absorbed by the cadmium ions from the solution at the right hand side cathode, and the cathode is being deposited at the right hand side electrode, that is cathode. So the net reaction is zinc releasing the electrons which are absorbed by the cadmium ions, and then zinc ions are released into solution, and cadmium metal is deposited on the electrode at right hand side electrode. Okay, so now we need to find out the EMF of the cell. Standard EMF of the cell is standard reduction potential at right hand side electrode minus standard reduction potential at left hand side electrode. So that is the standard electrode potential of cathode minus standard electrode potential of anode. So in case of right hand side cathode, right hand side cathode is cadmium, and therefore you can see that for cadmium it is minus 0.40 volt standard reduction potential, minus, now standard reduction potential for zinc electrode is minus 0.76. So if we carry out this summation, we get the result of 0.36 volt. So the cell which is connected in this pattern, that is zinc in contact with the cadmium, zinc and cadmium electrode cell, the cell standard electrode potential for such cell is given by 0.36 volt, and the cell reaction is given by this particular, or cell can be represented by this particular fashion. Okay, similarly the second example, we can take aluminum in aluminum electrode and silver electrode combination. So aluminum in aluminum solution, aluminum ion solution, which is connected to silver electrode in silver ion solution. Both the concentration of both the solutions are 1 molar, because they are standard electrode potential. And at anode, obviously left hand side electrode is anode, so aluminum has to act as anode, and at cathode there is a silver electrode. So at anode, what is happening now? Aluminum, it is releasing 3 electrons into the solution, and aluminum ions are going into the solution, and therefore these 3 electrons, these are being absorbed at the cathode by the silver ions, and 3 moles of silver atom, those are being deposited at the silver electrode, which is at the cathode, or at the right hand side. So the overall reaction is represented by this particular reaction, that is aluminum. It is releasing 3 electrons. Those 3 electrons are absorbed by the silver ions, and now aluminum ions are released into solution, and the silver atoms, 3 silver atoms are being deposited at the right hand side electrode, that is cathode. Now what is the standard reduction potential cell reaction? So standard electrode potential of right hand side electrode minus standard reduction potential of left hand side electrode. So we substitute the value of standard potential of cathode minus standard potential of anode. So standard reduction potential of cathode is 0.80, because at cathode there is a silver electrode. So silver, in you can see here that it is 0.8 volt. So 0.8 minus, and standard reduction potential of your aluminum is minus 0.11 minus 1.66 volts. So if I substitute it, it gives me 2.46 volt. So the cell EMF of this particular cell, that is aluminum with silver, is 2.46 volts. Okay. Similarly, we can have other combinations of aluminum in contact with the zinc. So aluminum will be on the left hand side, and zinc will be on the right hand side. So aluminum at anode, and zinc will act as a cathode. So at anode, what is happening? These 2 atoms of aluminum, they are releasing 3 electrons each, and therefore 6 electrons will be released at the anode. and oxidation will take place at anode. And at cathode, what will be happening? 6 electrons will be absorbed by the 3 atoms of zinc ions, and therefore 3 atoms of zinc will be reduced and it will be deposited at the cathode. So the net reaction will be that 2 atoms of aluminum will release 6 electrons. These 6 electrons will be absorbed by the 3 ions of zinc 2 plus, and therefore 2 atoms of aluminum ion will be released into solution and 3 atoms of zinc will be deposited at the zinc electrode at cathode. Overall cell reaction will be the standard electrode potential of right hand side electrode minus standard electrode potential of left hand side electrode. Obviously it is reduction potential. So the values are for right hand side electrode for zinc, the value is minus 0.76, which is over here, minus the aluminum standard reduction potential is minus 1.66, so it is given over here. So minus 0.76 minus of 1.66 will give you 0.9 volt. So the cell EMF of this particular cell aluminum in contact with zinc is given by is actually 0.9 volt. Okay. Similarly, I can connect the standard hydrogen electrode to copper electrode, which we have seen earlier also as an example. But then here again, the standard hydrogen electrode will act as a left hand side cell at anode. It will act as anode, and cathode will be obviously copper. So at anode, what is happening? This hydrogen is releasing 2 hydrogen ions into solution and electron. This electron will be absorbed at the cathode by copper ions, and the copper will be released and it will be deposited at the cathode, which is at right hand side electrode. So the net reaction will be this hydrogen plus copper ion will give you hydrogen ion and the copper which is deposited at the right hand side electrode. So again the standard standard EMF of the cell will be the electrode potential or standard reduction potential of the right hand side electrode minus standard reduction potential of the left hand side electrode. So I have standard potential of right hand side electrode for copper, it is 0.34 volt, and obviously since this is a standard hydrogen electrode, so standard reduction potential of standard hydrogen electrode is 0, and therefore minus 0.34 minus 0 volt is 0.34 volt. So whenever a cell is connected to a standard hydrogen electrode, the standard cell EMF is nothing but this cell EMF or standard reduction potential of the right hand side electrode, that is 0.34 volt. I can take n number of numericals based on this analogy, and I can find out the standard reduction potential or standard potential of a given cell as per the convention in this manner. Okay, let us move ahead. So basically this is very important concept of standard half cell reaction or arranging the standard half cell reaction. Now what happens, sometimes metals like platinum or gold, they are used as inert electrodes. They do not participate in the reaction but provide their surface for the oxidation or reduction of reactions, and they can be also used for the conduction of electrons. Okay, so exchange of electrons can take place. Now the standard electrode potential are very important, as we have seen, in order to understand their behavior in solution, because we can extract a lot of useful information from them. Now the values of standard electrode potential for some standard half cell reduction reactions are represented in this particular table here. Now this is a very specific way of representing the reduction half cell reactions, because we can make out various important conclusions from this. Now if the standard electrode if the standard electrode potential of an electrode is greater than 0, you can see here it is a standard hydrogen electrode. Now all the standard reduction potential above it are positive and below it are negative. So if the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable compared to the hydrogen gas. Okay, this you can see. So it is arranged according to its stability. Okay, so once again I repeat that if the standard electrode potential of an electrode is greater than 0, that is above this, then its reduced form is more stable compared to hydrogen gas. Similarly, if the standard electrode potential is negative, then the hydrogen gas is more stable than the reduced form of the species. Okay, so it can be seen that the standard electrode potential for say fluorine is the highest in the table. Okay, in case of fluorine, it is highest in the table. What does it indicate? It is indicating that the fluorine gas has the maximum tendency to get reduced. Fluorine gas has maximum tendency to get reduced to fluorine ions, and therefore fluorine gas is the most strongest oxidizing agent and fluorine ion is the weakest reducing agent. Got the point? Similarly, if you take the example of the bottom side, lithium. This lithium has the lowest electrode potential. What does it indicate? It indicates that the lithium ion is the weakest oxidizing agent, while the lithium metal is the most powerful reducing agent. Isn't it? So it may be seen that as we go from top to bottom, along the table, the standard electrode potential decreases, and with this decrease the oxidizing power of the species on the left hand side. You can see your oxidizing power on the left hand side, and increases the reducing power of the species on right hand side of the reaction. This is the left hand side of the reaction, this is the right hand side of the reaction. Okay, so electrochemical cells are extensively used for determining the pH of solution. You can determine pH of solution, you can determine solubility product, you can determine equilibrium constant, and you can determine any other thermodynamic property which is mean for the use in the electrochemistry. You can utilize this concept for potentiometric titrations as well. Okay, so you can have series and you can name it with the numericals which we have seen just now. You can see here that the just as an example, we have seen that this copper which is above this standard hydrogen electrode, so it has got positive standard reduction potential 0.34 volt, whereas we have also seen zinc, so it has got negative standard reduction potential. Cadmium, we have seen that it has got negative standard reduction potential. What does it indicate? What does it indicate? It indicates that this zinc or cadmium, they are more stronger reducing agent than the copper in this case as an example, or you can say that zinc or cadmium, they are weaker oxidizing agent than the copper which is having the higher position. You can also see the example of silver. This is the aluminum situated over here, and the silver which is situated over just now. We have seen the example, and when we connect these two cell, we have got the highest cell EMF, because now this aluminum is the weaker oxidizing agent and your silver is the stronger oxidizing agent. Or in this case, if you come on the right hand side, your aluminum is the stronger reducing agent and your silver is the weaker reducing agent that way. So I can find out many answers to the many important questions which are based on this standard reduction potential series. Now the basic concept is the standard hydrogen electrode is situated exactly at the center, because we have represented its cell potential as 0 and its cell EMF is as a 0 volt, and depending on this value all the other cells which are represented with respect to it. So whenever you connect this standard hydrogen electrode to any of the cell above or below, the corresponding standard reduction potentials which are getting or standard reduction potentials which are obtained in connection with this standard hydrogen electrode, that particular EMF will be represented, or that particular EMF is the EMF of the given cell which is connected to standard hydrogen electrode, is the concept. There are many questions that why I mean in corrosion chemistry or in corrosion thermodynamics also we can get the answers to many of our fundamental questions, that why always you can have a brass screw on these steel sheets, or which two metals can be connected with each other, or which two metals should not be connected with each other in direct contact with each other whenever they are present in the aqueous contact. And there are many more questions which can be answered based on this particular electrochemical series. Okay, so we will see the further applications of this particular knowledge of electrochemical series further in this particular lecture. So friends, we will stop here in this lecture 3, and in our coming lectures we will be seeing, or we will be looking for the applications of whatever knowledge we have gained with this electrochemistry discussion. Thank you.